Imagine you're diving into the complex world of data analysis, and you come across the term p-value. At first glance, it might seem like just another statistical concept, but understanding the p-value is crucial to making informed decisions based on data. The p-value is a probability score that helps you determine the significance of your results in hypothesis testing. It's the probability of observing a sample statistic as extreme as, or more extreme than, the one observed, assuming the null hypothesis is true. In simpler terms, it's a measure that tells you how likely your observed data would occur under the assumption that there's no effect or relationship present. The origins of the p-value lie in the realm of hypothesis testing. When you conduct a statistical test, you're essentially checking whether your data supports a particular hypothesis, known as the alternative hypothesis, or if it fails to reject a default assumption, the null hypothesis. The p-value comes into play as a decision-making tool, helping you decide whether to reject the null hypothesis. For example, let's say you're testing whether a new drug is more effective than an existing one. The null hypothesis might state that there is no difference in effectiveness between the two drugs. After conducting the test, you calculate a p-value. A small p-value, typically less than 0.05, would indicate that the observed difference in effectiveness is unlikely to be due to random chance, leading you to reject the null hypothesis and conclude that the new drug is indeed more effective. However, it's essential to interpret p-values carefully. A low p-value doesn't prove that the alternative hypothesis is true. It merely suggests that the observed data is unlikely under the null hypothesis. Conversely, a high p-value doesn't prove that the null hypothesis is true, only that the data doesn't provide strong evidence against it. In hypothesis testing, the p-value helps to avoid two types of errors, type 1 and type 2 errors. A type 1 error occurs when you incorrectly reject a true null hypothesis, while a type 2 error happens when you fail to reject a false null hypothesis. The significance level, commonly denoted as alpha, usually set at 0.05, is the threshold for deciding whether a p-value indicates a statistically significant result, thus controlling the risk of type 1 errors. Calculating p-values often involves statistical software, which can handle the complex mathematics involved. The calculation depends on the type of test you're conducting, e.g., t-test, chi-square test, and the distribution of the data. For example, in a t-test, the p-value is derived from the t-distribution, which accounts for the sample size and the variance in the data. It's also worth noting that the interpretation of p-values can vary depending on the context. In some fields, a p-value below 0.01 might be considered strong evidence against the null hypothesis, while in others, a p-value below 0.10 might still be considered significant. This variability underscores the importance of understanding the specific standards of the field in which you're working. The concept of p-value has also sparked debates in the statistical community. Some argue that p-values are often misinterpreted or overemphasized in research, leading to a false sense of certainty about the results. As a result, there have been calls to supplement p-values with other statistical measures, such as confidence intervals, to provide a more comprehensive understanding of the data. In conclusion, the p-value is a powerful tool in statistical analysis, helping researchers and data analysts make informed decisions about the significance of their results. However, it's crucial to use and interpret p-values correctly, understanding their limitations and the context in which they are applied. Whether you're testing a new medical treatment, analyzing economic data, or conducting any other form of research, a solid grasp of the p-value will enhance your ability to draw meaningful conclusions from your data.